from here, we want to transform the next function, right? The next function says what? When f of t is equals to t all raised to the power of n, meaning that we've come to the end of the standard table of Laplace, right? Once we've transformed this, meaning these are the possible functions we'll be seeing when it comes to what? Laplace transform. Now, given that f of t is equals to t all raised to the power of n, right? You know, this is the general formula. This is the integral formula that defines Laplace, right? Meaning, in this case, I have the Laplace transform of t all raised to the power of n is equals to integral from 0 to infinity. What's the f of t in this case? T all raised to the power of n, right? Multiplying exponential all raised to the power of negative st dt. All right. Now let's integrate this. You know, unlike the previous transform we did, which was sine 80, cos 80, sine 80, and cos 80, we said we are expressing this strict function in terms of exponential, right? So as to perform easier calculation. But in this case, is it possible for us to transform? Is it possible for us to express t raised to the power of n in terms of exponential? So as to perform what we did previously? It is not possible. This is we don't have that relationship, or we don't have that expression between t and exponential. So meaning in this case, you have to use by part. You have to use what? By part. And when we say by part, this is your u, this is your what? dv. But what I'll be using in this particular video, I'll be using the shortcut. I'll be using the other method to solve this, right? Then later on, I'm going to solve this using by part. So you've seen that for each of these functions, you finding their transform, you can actually use other methods to find it. Are you getting me? So that's what I'll be doing here also. It's not as if you can't find this function using by part. You will definitely get an answer, but I'm going to do that later. Now, from here, solving this your function using your other method, it is called the gamma function. You know, when it comes to integration generally, we have different form of integration, meaning we have different form of integral. It is called integral transform. Laplace is one of them, right? I said we have integral transform, meaning we are referring to Laplace, we are referring to gamma function, we are referring to Mellin function, we are referring to Leibniz function, we are referring to Taylor series, Macaulay series, a lot of functions. So you solving this, meaning mathematically it works, it is correct. What we're doing now, it means mathematically we are correct. All right. Now it is called the gamma function. When we say gamma function, by gamma function, we are saying that, looking at this is a gamma function. This gamma function, the result is what? N factorial. The result of this gamma function is what? N factorial. We are saying the gamma function, this is how you write your gamma function. We are saying the gamma function of n is equals to this integral function. The answer becomes what? N factorial. Now observe this. Observe what I'll be doing here. Let's say, you know, this is the gamma function of n. Now let's say the gamma function of k. The gamma function of k is equals to integral from 0 to infinity k always to the power of n, right? Multiplying exponential always to the power of k dk is equals to what? N factorial. Let's take one more. Gamma function of p is equals to the integral from 0 to infinity of p always to the power of n exponential always to the power of negative p dp is equals to what? N factorial. Now, what can you say about all of this? You observe that you are having t raised to the power of n exponential raised to the power of negative t with respect to dt. You have your answer as what? N factorial. For this second one, what do you have? K raised to the power of n exponential raised to the power of negative k dk. You have your answer as what? N raised to the power of n. You have your answer as what? N factorial. Similarly, you are having integral from 0 to infinity p raised to the power of n exponential raised to the power of negative p dp. You have your answer as what? N factorial. So this is what gamma function is saying. Meaning that if you have any function in this manner, the answer becomes what? N factorial. Your answer becomes what? N factorial. Now, check, this is by gamma function, right? Now check what we have here. What is the difference between this Laplace transform of t raised to the power of n and this gamma function? What's the difference? The difference is the power of the exponential. The power of the exponential. Meaning that gamma function works if the power of the exponential is having just single variable. It is having what? Just single variable. In this case, I would have implemented gamma function if my exponential is it exponential raised to the power of negative x or exponential raised to the power of negative t? I said in this case, we've seen that gamma function only works if you have exponential raised to the power of a single variable, right? Following what we did, this is just for raised to the power of negative t, negative k, negative p. Now, the difference between the Laplace transform of t raised to the power of n and these gamma functions is the power of the exponential, right? Now, I said this answer would have been equals to n factorial, true or false? But what we have here, this integral function, I would have had my answer. I said this integral function, I would have had my answer as what? N factorial. But in this case, I'm having what? Exponential negative st, right? And even I'm having exponential raised to the power of negative t. My answer is what? N factorial, following gamma function, right? Now, what we'll be doing here is that, what is the possible way in which you can write exponential raised to the power of negative st as exponential raised to the power of t, or exponential raised to the power of a single variable? Are you getting that at all? What we've been doing here is that, what is the possible way to write exponential raised to the power of negative st as exponential of negative variable, right? Of the exponential of a single variable, of the exponential of a single variable. Irrespective of the variable, we are still having what? N factorial, right? Irrespective of the variable, we are still having what? N factorial. Now, this will take us back to what? It's differentiation. Now, I would say that let u is equals to negative, I would say let u is equals to st, right? If u is equals to st, it becomes, say this is equation 1, right? Meaning, what I have here in equation 1, initially, what I want to achieve now is that the power of my exponential, I want to express it in terms of single variable. Irrespective of the variable, I will still have n factorial, right? The aim is that it should be a single variable. It should be a what? Single variable. Now I'm saying let u is equals to st, meaning equation 1, or you say this integral function becomes what? Integral from 0 to infinity t raised to the power of n exponential raised to the power of negative u dt. Say this is what? 2, right? But in this case, this is not a gamma function yet, right? This would have been a gamma function if I'm having t raised to the power of what? If I'm having u raised to the power of, if I'm having what? U raised to the power of n, and I'm having what? Du, right? Now, what this is telling us is that I have to solve this. I have to do some manipulation here, or I have to do some necessary solving. Now, from here, from equation 2, what we are going to do Okay, I said integral from 0 to infinity t raised to the power of n exponential r raised to the power of negative u dt. So this is equation 2, right? Now, what we'll be doing is that we are going to say from here, from this guy, what I want to do from here now is that I'm expressing t as what? U, right? And I'm expressing the t as what? Du. Now, from u is equals to st, we have u is equals to st. Make t the subject of the formula. It becomes what? Divide both sides by what? T. Therefore, t is equals to u over s. Let's say this is equation 1, right? Meaning, anywhere I see t, I'll substitute u over x. Moving on, from this same equation, which is u is equals to st, differentiate with respect to t, meaning du dt. Now, by du dt, what's our answer? Du dt is equals to x, cross multiply. It becomes what? Du is equals to what? S dt. Divide both sides by what? X. Divide both sides by x. Therefore, dt is equals to du over x. Call this 2. Meaning, back to equation 2. The equation 2 you have initially. You found t, right? And you found what? The t. Now, substitute. It becomes integral from 0 to infinity. What's your t now? U over x, only to be always the power of what? N, multiplying exponential negative u. What's the t? Du over x, right? From here, I have integral from 0 to infinity, right? U raised to the power of n, u raised to the power of n over s raised to the power of n, multiplying exponential r raised to the power of negative u, multiplying what? Du over what? X. By gamma function, we are saying integral from 0 to infinity t raised to the power of what? N, multiplying exponential of negative t dt is equals to what? N factorial. Now, meaning that up to this level, I must express this integral function in this manner. So by doing that, I'm going to factor out x, right? Any question? I'm going to what? Factor out x. So I'm adding integral from 0 to infinity u raised to the power of n, multiplying exponential r raised to the power of negative u du, right? I'm having 1 over x raised to the power of n here, right? 1 over x raised to the power of n multiplied by what? 1 over x. Any question? 1 over x raised to the power of n is a constant. 1 over x is a constant, right? Meaning I'm having 1 all divided by indices. This becomes what? S plus 1. Integral from 0 to infinity u raised to the power of n exponential r raised to the power of u du. And we said by gamma function, this is what? N factorial. That is 1 over x raised to the power of n plus 1 multiplied by n factorial. This is equals to what? N factorial all divided by x raised to the power of n plus 1. Can you see how it works? So you are saying the Laplace transform of t raised to the power of n is equals to what? N factorial all divided by x raised to the power of n. So this is the other method which you can use to find the Laplace transform of this guy. You can also use the normal method which says that t raised to the power of n multiplying exponential r raised to the power of negative st dt, right? Which is by part. Which is what? By part, right? So that's it. Now let's take example on this. But I said it that this works mathematically. This is correct. We have a lot of integral transform. We have what? A lot of integral transform. Out of all these integral transform, we have Laplace transform, we have Mellin transform, we have Leibniz, we have Taylor, we have series, we have a lot. So okay, we have gamma, right? So we make use of gamma so as to transform t raised to the power of n. So mathematically you are correct. You can use it anywhere, anytime. You are correct. Now let's take these examples. Find the Laplace transform. Find the Laplace transform of t all raised to the power of 4. Find the Laplace transform of t all raised to the power of 4. Your answer to this, what's the answer? The comparison between the Laplace transform of t raised to the power of n. We are saying t raised to the power of n transform becomes n factorial all divided by x all raised to the power of n plus 1. So similarly, the Laplace transform of t raised to the power of 4, it becomes what? 4 factorial all divided by what? X raised to the power of 4 plus 1. By 4 factorial, meaning that 4 times 3 times 2 times 1 all divided by x raised to the power of 5. What's the answer to this? 4 times 3 times 2 times 1, what do I have? 24. So I'm saying the Laplace transform of t all raised to the power of 4 is equals to 24 all divided by x raised to the power of 5. So this is how it works. So far we've been able to transform the possible function we'll be seeing as far as Laplace is concerned. Any questions so far? Alright, so in the subsequent video, we'll be solving, in the subsequent video, we are going to look into the theorem of Laplace, right? Meaning that we'll be looking at what? The first theorem. We'll be looking at the first theorem, which is what? Multiplying by exponential function. The second function, which is what? Dividing by t function. And the third one, which is what? Multiplying by t all raised to the power of n function, right? So what this theorem is saying is that given a function, I already know that all these functions exist in Laplace. Now, given a possible question, what techniques would I implement? What techniques of Laplace am I going to implement? So this is what the theorem is saying. This is what the theorem is saying. All right.